Okay, so we begin on page 31. We'll first take our look at the calendar. Calendar is getting shorter and shorter in terms of what's left. Today we talk about Taylor polynomials. Next class, Taylor series. The class after that, more Taylor series. So apparently this Taylor thing is important. It's the next 3 classes. That's all this week. Monday coming up is our review day for Wednesday's test. Also coming up is project number 8 that is going to be due on Friday. And quiz number 7, also happening on Friday. Again, I'm going to try to do something so that we don't have to have 2 things at the same time, but I don't know what that thing will be. It might be another one of those where the quiz becomes a in-class work with your neighbors thing. Any questions on the calendar? Okay. Then let's take a look on page 31. And we'll start up here, Sam, in this section. It's in the middle of the page. Okay, do you guys remember we started last class? I showed you on GeoGebra up here a graph that looked like sine of x. And then we looked further and further, and all of a sudden it didn't look anything like sine of x. So the goal today is to figure out how do we find the equation for the thing that looks like sine of x for a while, but then changes quite dramatically. That's what we're after today. Now, this thing right here was written to be a big old long group activity. We could also do it together up here on the board. So are you feeling motivated? Group thing is wonderful as long as we're feeling motivated and we can push through because it's long and we got to make sure we're focused and okay. All right. So let's do this. Let's do this together. Josiah, consider. Okay, I'm just going to highlight f of x equals e to the 2x. We're going to be playing with 2 functions in this problem, and that's one of them that's really important. E to the 2x. That's the f function. Okay, number 1. Let p sub 1 of x, don't worry about the 1 for the time being, be a degree 1 linear polynomial. All right, so back in some algebra classes, you guys maybe wrote linear things as y equals mx plus b. We're going to write it using just different letters. We're writing it as a sub 0 plus a1 times x instead of mx plus b. Same, yes? Just changing the letters. So that right there is what we are calling p sub 1 of x. It's just a generic line equation. A0 and A1 are constants. Let's go to part A. We're going to compute f of 0 and f prime of 0. Again, f is highlighted here in yellow. So f of 0, e to the 2 times 0, which is 1, right? E to the 0 is 1. In order to find f prime of 0, what do we first need to find? Yeah, first we need to find the derivative. Again, f is highlighted there in yellow. What's the derivative of e to the 2x? 2e to the 2x is good. That's our friend the chain rule. And then we can find f prime of 0, plugging 0 into that equation. It is 2. Yeah, so far so good. Okay, part B. Now let's forget about the f function, but let's go back to the p sub 1 function, which was our generic linear function. I'll highlight p sub 1 in green here. Okay, so we're going to do p sub 1 of 0. Let's do that now. P sub 1 of 0. P sub 1 is just our green function. We're plugging 0 for what letter? X. So we plug 0 in for x. There's an a0 plus a1 times what? 0, which is a sub 0, done. The next thing we're asked to find is p sub 1 prime of 0. What do we first need to find? P sub 1 prime of x, right? We got to do it in general, and then we'll plug in 0. And again, p sub 1 is highlighted in green. What's the derivative of that linear function? It's just a sub 1. Right? No x's left over. So it's kind of funny, but I could then find p sub 1 prime of 0, which is what I'm asked for. What is it? It's a sub 1, because p sub 1 prime of anything is a sub 1. All right, so lots of symbols. Any questions so far? Okay. Here's where we relate these two seemingly unrelated things. We have our function f of x. It is just e to the 2x, exponential growth. Then we have this generic line function. And we're going to jump here to part C. Goal. Okay, let's pause right there. Lots of symbols again. The goal is to make it so that these two functions agree with each other at 0. That's this part. P1 of 0 is supposed to equal f of 0. I want them to hit the same point. And I want their derivatives to be equal to each other. So I want them to have the same slope as functions. Okay, so let's do that. So we're setting the purple things equal to each other. On the one hand, f of 0 was 1. On the other hand, p1 of 0 was a sub 0. I want them to equal each other. So how much is a sub 0? 1. Super. And we'll come over here in black. What was f prime of 0? It was 2. What was p1 prime of 0? It was a sub 1. I want them to be equal to each other. So what is a sub 1? So let's see. I will circle here in red. It was these two pieces gave us this guy. And in green, these two pieces make them equal. And we got that equation. So all we're going to do now is just write down what p sub 1 of x is. Again, p sub 1 is highlighted up there in green. What did we figure out a0 needed to be? 1 plus, it says a1x. What was a1? 2. 1 plus 2x. Anybody know what that 1 plus 2x equation represents for my e to the 2x function? Well, that is true. It is exactly what it says. Yeah, that's the tangent line at x equals 0. We wouldn't have done the tangent line this way, but it's equivalent to what we would have done. You would make sure the tangent line hits the function, right, at the point. That's what we did over there in purple. F of 0 was 1. You made sure the tangent line was also 1 at the same point, at 0. And then you would make it so that, well, we made the slopes equal. Really what we would have done was found the slope. We did that up here, right? This is the derivative of e to the 2x. Plug in 0, because that's the point we're focusing on apparently. The slope is 2. Where do you see the slope of the tangent line being 2? Right there, right? So that's the equation of the tangent line. No problem. So does this process seem familiar? Yes, it is the process of finding a tangent line. Question so far? Okay, so that's a whole lot more work than finding the tangent line the normal way. So I'm not saying this is an improvement to our old way of finding a tangent line, but now we're going to go beyond tangent line to a place we haven't gone before. So we'll start here in number 2. We now have a new function, p sub 2 of x, which is going to be a0 plus a1x plus a2x squared. I'll highlight this guy in blue. P sub 1 was a generic line. What is p sub 2? That's a parabola, and it is a generic parabola, right? A0, A1, A2 are constants. That could be anything in the world. This is a generic parabola formula, right? I mean, it doesn't look quite like the generic parabola formula that we're used to writing, ax squared plus bx plus c, right? But it's the same, we're just changing the letters. Okay, let's in green find f double prime of 0. So f is still the function that's off my screen. What is f? E to the 2x. We're going to find the second derivative at 0. What do we first need to find? Second derivative as a function. So the second derivative we'll get from the first derivative. For me, it's in the top right here in black. F prime of x was 2e to the 2x, so find another derivative of this guy, right? We want the second derivative. What is f double prime of x? Is 4e to the 2x, right? Just multiply by another 2 with the chain rule. F double prime of 0, therefore, is how much? 4, right? Okay, so we've got f double prime of 0 is 4. What is that a measure of in terms of the f function? Like what shape kind of word does it have to do with in terms of the graph? Concavity, right? First derivative talks about increasing, decreasing. Second derivative talks about concavity. This function is concave what at 0? Because that's a positive 4. We know concave up. Okay, so second derivative is 4. Great. Let's go to the next page. And we're going to compute for our p sub 2 function. I'll write p sub 2 up here just so we've got it. P sub 2 of x is a0 plus a1x plus a sub 2x squared. So what we're going to do here is find p sub 2 of 0, p sub 2 prime of 0, and p sub 2 double prime of 0. Let's first find the derivatives. P sub 2 prime of x. So I want the derivative of this thing. What happens to the a0 when I take a derivative? A0 is a constant, so the derivative is nothing. What's the derivative of a1x? A1 plus the derivative of a2x squared. A2x? 2 a sub 2x. Do we see that? A lot of symbols, but the derivative's easy, right? You take the x squared, you bring the power, the 2 in the front. The a sub 2 is a constant multiple, it just sits there. Decrease the power by 1. Any questions on that? Okay, this is so much fun. Let's find one more derivative. What's the derivative of a sub 1? 0. The derivative of 2a sub 2x? 2a sub 2. So far, so good. Any questions on our derivatives? Okay, now according to the directions here, we're supposed to find p sub 2 of 0, p sub 2 prime of 0, p sub 2 double prime of 0. So we're just plugging 0 into these 3 black formulas here. So the first one we'll plug in up here, p sub 2 of 0. What is it? 1 vote for a sub 0, is that right? Everything else disappears. This one here, p sub 2 prime of 0, is a sub 1. Any questions on that? And this is the funny one, p sub 2 double prime of 0. It's 2a sub 2. There's no x to plug anything in. So it's just 2a sub 2. It's always 2a sub 2. Question so far? Okay, so here's where this has nothing to do with the f function. This is just a generic parabola with two derivatives and plugging 0 into all three of those formulas. But now we're going to relate it to the f function, which again was our exponential e to the 2x. And we're going to make it so that the e to the 2x has the same value as the function, this p function. So it's going to agree with the purple. It's going to have the same first derivative. It will agree with the black. And it's going to have the same second derivative. It will agree with the green. So let me just write some stuff here so that we've got it on the same page. I'm going to put a little line here. Somebody remind us from the previous side, what was f of 0? It was 1. What was f prime of 0? That one we found already was 2. And then f double prime of 0 we just found on the bottom of the previous page is 4. Did everybody see where we're getting these numbers from? So we've got kind of these two parallel tracks happening. You can find anything you want about the original f function. That was the e to the 2x. That's on the right-hand side. Then we've got this generic parabola formula, which has nothing to do with e to the 2x, right? Parabola, e to the 2x look nothing like each other. And we're going to take these two parallel tracks and make them equal every spot. So we're going to make the purple things equal to each other, the black things equal, and the green things equal. So let's make the purple things equal. What does that say? It says a sub 0 is 1. Then we'll make the black things equal to each other, which tells me that a sub 1 is 2. And then finally we make greens equal to each other. This one, we'll have to do a tiny bit of work, but the green says that 2a sub 2 is supposed to equal 4, which means that a sub 2 is really 2. Any questions on the process? It's a funny thing to do, but it's not hard, right? Just have to keep track of sometimes the indices here, the sub 1, sub 2, sub 3, they can be intimidating, but they're just constants. Mm-hmm. Yeah, we would have put 6 in for those things. Good. Yeah. So let's write something down. So let's copy down the p sub 2 formula now. P sub 2 of x. My p sub 2 formula is the very top thing on the smartboard, but I now know what the a0, a1, and a2 are if I want to make this parabola agree with my e to the 2x function, at least near 0. So it used to be a sub 0. What is a sub 0? Is 1 plus a sub 1x, 2x, plus a sub 2x squared, 2x squared. Okay, so how about we actually take a look at the graph of these two functions here and see if they actually look good. So we could use GeoGebra. We'll use the graphing calculator so you can follow along if you're interested. So I'm going to go in here, and the first function I'm going to graph is just e to the 2x. Second e to the 2x. So standard window maybe is okay. I'm probably going to focus in a little bit closer on this thing. Maybe we'll go like, maybe something like -3 to 3. And a 0 on the bottom because the e to the 2x is always positive. So I think we'll get an okay picture here. Okay, that seems fine. Then I'm going to graph p sub 1 of x, which was on the previous page. What was p sub 1 of x? 1 plus 2x. And I think we've already decided that's just going to be the tangent line at x equals 0. So I will graph that, and we will see our tangent line. Great. And now we're going to graph the new thing. We've already done the tangent line before, but now we're going to graph this guy right here, this parabola. 1 plus 2x plus 2x squared. plus. Yeah, there was, so the f double prime of 0 was 4, but we had to make it equal to the other green thing. Okay, so let's take a look. Here comes a parabola. How does that parabola look? Maybe I'll go back. I'm gonna make the first one thick just so we can really see it. So the thick one is going to be our original function, the e to the 2x. Then we're going to see the tangent line. And then finally the parabola. And how does that parabola look relative to the e to the 2x function? Looks pretty good near x equals 0. And if we zoomed in far enough, you actually wouldn't be able to tell them apart. We'd have to be really zoomed in, right? We can clearly see the parabola here running away from the e to the 2x. But this is the best parabola possible in terms of trying to make it look like e to the 2x at x equals 0. Garrett.
When I accidentally did it with a sub 2 equals 4.
The 4x looks better? The 4x squared?
Yeah.
All right, Garrett. All right, Garrett tried this one here. Okay, so maybe, all right, so the parabola matches up pretty well with the e to the 2x over here. And I think, Garrett, you said something good. You said maybe not near x equals 0. So near x equals 0, this isn't as good as what we had before because you can see the parabola just barely gets there. I think we matched up with the e to the 2x a little bit better over on this side. So you can make a parabola that looks better in different spots. We found the parabola that looks best right at x equals 0. Okay, next observation. What was true about the a sub 0 and the a sub 1 that we found in the first part when we did the tangent line compared to those constants when we did the parabola? They were the same, weren't they? I mean, you can see it up here. We graphed both of them. The tangent line was 1 plus 2x. The parabola was 1 plus 2x plus some x squareds. So it turns out you don't need to, like we redid everything here, but it turns out you don't need to. As soon as you find the value of some a, it's going to be the same a even as your power gets higher in the next round. So I think we've answered here this question. The a sub 0 and the a sub 1 are the same. And so that means that when we come down here to number 3 has a formula called p sub 3, which is a generic cubic. Right? It's not a parabola anymore. It's a generic cubic function. That we can say definitively that the a0 that we're going to get here is going to be the same a0 we got before. It's still going to be a 1. And the a sub 1 is still a 2. And the a sub 2 is also a 2. The a sub 3 is the part that's new for us. We don't know that yet. So let's just find that. So we want the third derivative of f. And I will remind you that the second derivative of f that we've already found was 4e to the 2x. We did that before. What's the third derivative? Is 8e to the 2x. Therefore, we can plug 0 into this guy. We just keep plugging 0 in. That was a choice that was made in the beginning of this problem. What is the third derivative here? 8. Good. Now we're going to come down here to p sub 3. And we're going to find the third derivative of p sub 3. All right, but how about we save ourselves a little bit of time and not have to start from the beginning? When you take the first derivative of p sub 3, what's going to happen to this term? It's going to disappear. So I'm going to ignore it. When I take the second derivative, well, let's think. The first derivative of this would have been just a sub 1. What would the second derivative be? 0. I'm going to ignore that too. What would the first derivative of this one have been? 2a sub 2x. What's the next derivative? 2a sub 2. What's the third derivative? 0. In fact, the 2a sub 2 we calculated right up here. So if I just did one more derivative of this guy, it would be 0. So the only part that's going to matter to me is the x cubed part. That's the only one that's still going to be around when I take 3 derivatives. Third derivative at x. Okay, so let's try this here. I'm going to write down the first derivative. It's going to be some stuff I don't care about. And then finally, what's the first derivative of the last term? 3a sub 3 x squared. Then the second derivative of that one, stuff we don't care about, 6a sub 3 x. And then finally the third derivative, which one? 6a sub 3. That guy without the x. I'm going to plug 0 in because I plugged 0 into the f derivative, so I better plug 0 into the p derivative, but it's silly because there's no x's left over anyway. So what do we get when we plug 0 in? 6a sub 3. And so if I want my f function, my exponential, to have the same third derivative as my cubic function here, then what's our equation to solve? 6a sub 3 equals 8. We need those two guys to equal each other, right? We just make them equal. Good. So a sub 3 is 8 over 6, or 4/3. So again, I'm going to graph stuff on the calculator, but let's first write our formula now. P sub 3 of x. The best cubic we can find to match up with that exponential function. Okay, it starts up here at the top with a0. It's still how much? A0 is 1. It has always been 1. It will always be 1 for this function. Plus a sub 1x. That's 2x. Plus a sub 2x squared is 2x squared. Plus the new part, a sub 3x cubed, 4/3 x cubed. I'm just going to underline this part right here, and then we're going to go to the calculator. Where have we seen this 1 plus 2x plus 2x squared before? That was the best parabola that we found. And then we're just adding another term. 1 plus 2x plus 2x squared. Why am I in finance? 1 plus, thank you, 1 plus 2x plus 2x squared plus 4/3 x cubed. That's okay. It'll take care of the division first and then the multiplication last, which is what we want. Okay, so it's going to regraph all of them. That's our original e to the 2x. Then we'll get our tangent line. And we'll get our tangent parabola, if that phrase makes sense. And then finally our tangent cubic, which I barely saw, which is actually a good thing. Why did I barely see it? Because it was so close to the e to the x function for a while. All right, so let's see if we can see a little bit more of this guy. Maybe I need to go down a little bit. So how about we try like maybe down to -10. And then I'm going to get rid of the tangent line. I'm going to get rid of the parabola too. I really just want to focus on the original and then my new cubic. And I'm going to get the original back to a regular old line. There we go. So if you are here and you want to select which ones to show, you just need to highlight the equal sign with the left arrow, and then the enter key toggles it on or off. You're welcome. Okay, so our regular e to the x, and then we're going to find our approximating cubic. Here it comes. looks pretty good like e to the x, and then eventually runs away from it, but it looks good for a while. And that is the best cubic to approximate e to the 2x near x equals 0. All right, can you guys do this next piece? I want us to find a formula for p sub 4, the Taylor polynomial of degree 4, that approximates this f function near 0. So if you understand the process, you won't have to do everything over, just the last coefficient. Give it a shot. Okay, so I think that on the previous problem, a bunch of folks got 2/3 for that next coefficient. Any questions on getting the 2/3? All right, and then some folks were able to generalize really readily, which is super. So what was happening here, if you look at the example you just did with the 2/3, it was really 16 divided by 24, right? That's where the 2/3 came from, was 16 over 24. And the 16 is a power of 2. The previous number was 8. The one before that was 4. So these are all the powers of 2 because those were the derivatives of e to the 2x. And then the 24 is really 4 factorial. And again, we see these factorials pop up maybe in an unexpected place. And when you take derivatives, like if you take a derivative of x to the 4th, which is what you did, why was it 24? Let's write something down here. If you start with x to the 4th and you take a derivative, what's the first derivative? 4x cubed. What's the next derivative? It's 12x squared. I'm going to write it the way Chris wrote it, which was this. It is 12, but it's really 4 times 3, right? And then what's the next derivative? X to the first. And then the next derivative, 4 times 3 times 2 times. And really that 1 comes down and then the x vanishes, right? So yeah, it's a factorial. That's the pattern. And multiplying the numbers maybe hides the pattern. Okay, so what does that mean we can do? Well, if you're good at using the calculator, you can get this guy to go out as pretty much as far as you want. So how about we try this? So you don't need to copy along here, but you can check out the video if you're interested. So I'm going to clear all these guys. I'm going to come up here and I'm going to try to type in this thing, which is a very complicated thing. But let's give it a shot. So the first place to go is second and then list. We are looking for the sum command, which is over here in the math menu. It's right there. So that's the word for series, summation. And then I need to tell it that I'm about to type in a pattern, and the word for pattern in the TI-83 is sequence. It's also in second list, but now it's here in the middle option, which is ops for operations. Sequence command is down here for number 5. And now we got to type in this generic formula here. So 2 to the n over n factorial x to the n. Literally, that's what I'm going to type in. 2 to the alpha n. Where's n? It's right there in green on mine. Divided by n factorial, alpha n. And then the factorial is inside of math. And it's over here under probability. It's there, number 4. So that's the 2 to the n over n factorial times x to the n. That's what we type. X to the alpha n. Okay. The rest of the sequence command says comma. Then you tell it what the variable is. What's the variable with respect to that summation? It's n. N is going from 0 to infinity, right? So the variable is not x. The variable is alpha n, comma. What's that? Yeah, and then 0 up to, you know what? Let's put a different, so I can't put a comma infinity here. So what I can do is put comma 5, and that would give me the sum of the first 5 terms. And that's it. You can put parentheses to close it, but that's the full command. And this right here will graph for me the original e to the 2x, as well as the best 5th degree polynomial. So let's give that a shot. So there's e to the 2x. And now it's got to do a lot of calculating because it's finding, see how slowly it draws? Because it had to find point by point everything on this 5th degree polynomial. And I can't really tell it apart from the e to the x, right? It looks the same here. The e to the x, I know asymptote's out there, so definitely it changes at this spot, but gosh, it's hard to tell it apart from e to the x. So how about we, so the nice thing about typing this in is that I can then very easily change this to, say, an 11, and it will find me the 11th degree polynomial without me having to go in and do all the coefficient calculating again. So in order to tell what's going on here, I'm going to change the window. I'm going to look even higher because I couldn't tell it apart up at 10. How about we go up to, I don't know, 50 maybe? And let's just see what this looks like. So there's our e to the 2x there, and then we're going to see the 11th degree polynomial. I don't know if you saw it. It came in. Do you see it here? So it came in very slowly here. Now I don't think we're going to see it for a while because it's going to be so close to the x-axis that we're not going to see it. But why is that a good thing that it's very close to the x-axis? Because so is e to the 2x. And then eventually it's going to come up here. Now, which one is going to grow faster, the e or the x to the 11? The e. So I'm maybe thinking I'm going to see the x to the 11 one maybe kind of bleed out just a little bit under because it's not going to grow as fast. But, you know, maybe on this window, I won't see it at all because it's so close to the e to the 2x. Any questions on this? Yeah, so the right way to do this is actually to use GeoGebra because then you can change the window very easily. So maybe while it's thinking, I don't know that we're going to see anything else there, but we can do this really easily on GeoGebra. In fact, so easily it's gonna seem like cheating, but options. All right.
So Ian, even though that graphing calculator is a program on your computer, it's still looking at us.
Yes, it's emulating the graphing calculator, including slowing down to. Yeah, well, you can. So here we'll try something else. So if I change this to like a 21, then it would go really slowly, right? Really slowly, point by point. So it'll graph the first one. But in fact, why don't I not even graph the first one? I just want to see the x to the 21 part. So it's going to graph it really, really, really slowly. But if I, let's see, I'm going to hit graph. I'm going to come in here and change. There's an option here that right now it says restrict to actual speed. But if I uncheck that, then you can see how quick the Knight Rider thing is moving here. And then it auto shuts off very fast. But down here, you can do this quite easily. So we can just type in our e to the 2x function. That does not look like e to the 2x. What did I do wrong? E to the 2x. Okay, that looks better. And here's the nice thing is that there's just a Taylor polynomial command. So we don't have to know what we're doing. We just type it in. Now, I always forget the notation, so I hit enter and I let it yell at me, which gives me what I need. So the function, the x value that you're centered at, and then the order number, which is the power that you're after. Okay, so the function in this case was just f. 0 was where we decided to focus our attention today. And if we wanted, for example, the 3rd degree Taylor polynomial, it's that one. If instead I wanted it to be a 4th degree, we just have to change this right here to a 4, and it's that one. But even better than all of that is if we come in here and make a slider. The slider is going to be the thing that's going to be the power that I want. So I'm going to go from 0 to 50 by 1s. And if I come back up here and change this guy to, instead of the 4th power or the 3rd power, I'm just going to type in the a power. Then I can just drag this guy to the right and it will zip through all the different powers. And so you can see how it's really following, right? Like on the left-hand side, you can see it following better and better. Now, there's also interesting stuff. All right, so then up to 50, I can't tell it apart. So we'd have to really kind of pull this thing into, okay, so there. It looks pretty good until, you know, -8, -9, something like that. But it also, it's also trying to hug it to the right, but we can't even see that it's not great because they both are off the screen. Okay, there we go. So which one is the e and which one is the x to the 5th? E is the higher one, right? We know e is going to win. So as I go higher power, okay, so they're up to 11. I can't tell them apart. What can I do to tell them apart? I can drag this guy down. Okay, good. So now I can see them apart, but I got to be up at like 10, 20,000 to see them apart. And if we this, you can see that the power is just right. It's just going to try to catch up to that e function. And then they're still looking good. I don't know what number that is. All right, so e to the 9, what is that? Or 10 to the 9? Those are billions. All right, so up there in the billions, we can finally see them apart. This is the 25th degree polynomial we're just watching here. As I increase the power, it's just going to keep chasing, and it will chase as long as you have patience to do the calculations.
So these Taylor series seem like they must be better at overall approximating functions that have like even or odd symmetry.
It doesn't have to have any kind of symmetry.
Well, because I mean, just on the right side, it's very close to e2x billion.
Mm-hmm.
But on the other side, I mean, it's much worse fit, obviously, because e2x doesn't have the symmetry.
So I would say, so Garrett is talking about how you know, we had to go really far to tell that it wasn't perfect on the right-hand side, whereas we didn't have to look very far here. I would put out there that maybe we should be thinking about how much the percent error is. So if you're off by, you know, like 100,000 on the order of billions, that's really good. If you're off by, now we haven't compared over here, but these two guys over here on the left-hand side are going to be teeny, tiny close to each other that even if you zoom in, you might have to pull it apart to the order of like microns in order to be able to see them apart. So I do think there's a good fit thing happening on the left as well as on the right. We're kind of diluted because as you said, it just looks, I'm trying to undo some more stuff here. There. That is too much undoing. There. So as you said, you know, like on the left-hand side, we can just see that it looks really good, but you know, how good is it? Well, let's see if we can pull them apart, but now going the other way. Does that make sense, Karen?
Yeah.
So I'm just like, how far do I have to go to pull these guys apart? All right, so here I'm on the 0.05 range, and if I do that, now I'm going to have to pull apart even more. So I still think there's like a, you know, like there's a really good fit happening out there. It maybe isn't as dramatic as what you were seeing here, but I think it's equivalent in terms of like how good the fit is. Yeah. Okay. So that is Taylor polynomials. Okay, so let's talk about what's happening here in general. So I'm now down to number 8. It has the Taylor polynomial formula for a general function f. Instead of dealing specifically with e to the 2x, now it's a generic function, any old function f. And right here is the wonderful formula for the nth degree Taylor polynomial. So what's going on? For us, what was the, first of all, what was the value of a for all the calculations we did? There's an a here, there's an a inside the function. It was 0 for us, right? We had x squared, x cubed, and we plugged 0 into all those derivatives. So for the problem we just did, a was 0 throughout. Great. The next thing that we see here is the third derivative at 0. What was the third derivative at 0 for our function? Just go back and find it. Third derivative at 0 was 8. And then how did we figure out what number to put in front of x cubed? What was a3 for us? It was 4/3. That was after we reduced it. What was it before? It was 8 over 6, and 6 is a factorial. What factorial is it? It is 3 factorial. So that's really what was happening, even though maybe we didn't see that pattern at the time. It was 8 divided by 3 factorial. It was the third derivative divided by 3 factorial. In general, it's the third derivative divided by 3 factorial. That's the number you put in the front. And the previous one was the second derivative divided by 2 factorial, first derivative divided by 1 factorial. This bothers some folks seeing a 0 in the bottom, but conveniently 0 factorial is defined to be 1, so make sure you don't get bothered by having a 0 factorial in the bottom. But this right here is our formula, and we're going to use this formula. Now the good news is this formula is on the reference sheet that is on the first page of this packet. Not the separate one with the big table, but actually attached to this packet. Go back to page 1. See it right there at the top? page 1 of this packet, you'll find a separate reference sheet. It's not the one with the big table, but at the top of page 1, you'll see that formula right there. Everybody find it? And again, you're going to bring this with you to the tests and the quizzes. It's page 1 of, oh, you don't have page 1 handy.
Is that table on Moodle? The other reference sheet.
I think the table is on Moodle, yeah, as a Word document. Yeah. Okay. So let's see if we can use it. Let's do this. F of x is cosine of x near x equals pi of degree 8. Lots of funny stuff happening here, but let's see if we can do the calculation. First of all, when we say near x equals pi, we are telling you that a, the value of a is pi. So whatever, you see the word near, that's the a. Okay, so in order to do our calculations here, we're going to need to find a lot of derivatives. We need to get up to degree 8. So we got to find 8 derivatives here. What's the first derivative of cosine? Negative sine. Second derivative? Negative cosine. Keep going merrily along. You need 8 derivatives there. Just to remind you notationally, when the derivative gets past 3, those primes are hard to read. So one way to write it is the derivative, but it's got to be in parentheses. So that symbol is how we write fourth derivative. Once you've got your 8 derivatives, you're going to make a new column where you find f of 0, f prime of, oh, I'm sorry, not f of 0, but what's the a value in this problem? It's pi. So we are doing f of pi, f prime of pi, f double prime of pi, all the way down. You need 8 numbers here. Okay, so we've found our 8 derivatives. We plug the magic number in this case the magic number was pi, that's given to you. Plug pi into all 8 of those things and the original function. Then we take each of those guys and divide it by the right factorial. And then according to the formula, the last piece of this puzzle, so what we've just done here is calculate a whole column. I'll circle it in green. The green column is this guy. We found the correct derivative, we plugged pi in, and then we divided by the correct factorial. But next to that is supposed to be x minus a to the power. So then next to each of these guys, I'll put here in black, this is x minus, how much is a? Is pi to the n. How much is n in that top row? It's actually 0. This one is x minus pi to the first. X minus pi to the second, and then keep going here. So it just has to be x minus pi to the right power. Probably didn't need to go out to 8 on this one, did I? Maybe 6 is enough. X minus pi 8. And so then I'm going to show a geometry sketchpad thing here, but if you wanted to type something into the calculator to see a polynomial that matches up really well with the cosine function, which isn't anything like a polynomial, here's what you do. You just start with f of x equals, what was my first term up there in green and black? -1 times x minus pi to the nothing. It's just -1 plus, what's the next term? Yeah, so then there's a 0, which we don't even need to write, but then the next one is a 1/2 x minus pi squared. Plus, the cubic term is 0. Then the fourth one is -1 over 24. So let's make that -1 over 24, x minus pi to the fourth, plus. And then you just have to write some more stuff, right? This one is going to act like this cosine function near pi, not near 0. So let's look at the picture. So this is here. Okay, there's your cosine function. I'm going to start showing you the graphs of these blue things down here. So the first one is going to be f of x equals -1. What kind of a graph is that? That's going to be a horizontal line. So at -1, there it is at the bottom. Now that looks really good in terms of hitting the cosine curve here and here and here. Which one of those three is the one that we're really going to be focusing on? This is the one on the right. This is x equals pi right here, okay? And then we're going to look at the degree 1. Now what was the degree 1 term here? It was 0. So when I hit this next button, it will appear like nothing's happened just because that's also the degree 1 approximation. But when we hit the next one, then we're going to add a 1/2 x minus pi squared, which will give us this. And you can see that light blue thing is looking quite good near x equals pi. What's going to happen when I hit the cubic one? Nothing, because it's 0. Next one is the 4th degree. 5th degree is nothing. 6th degree. 7th is nothing. 8th degree is that one. 9th degree is the same. And so you can see that dark brown one looks quite like the cosine curve for a while. And Chris had asked about, error tolerances. And so how long does it look like the sine curve, or the cosine curve, I should say. So let's hide this stuff here. And I'm going to click on this guy. All right, so here's our tolerance. Tolerance is 0.01. So when I click this guy and hit the plus sign, it's going to show me that this bottom approximation is quite good inside of these gray rectangles. So if you are very near x equals pi, then that approximation and the cosine curve differ by less than 0.01. They're really close to each other. And now if I hit the plus sign again, nothing changes because the linear approximation is the same. But now watch those black or those gray rectangles as they get wider, or actually most of them disappear because now we're really only focusing on this one at x equals pi. And as long as you are someplace inside of this rectangle, the blue parabola and the cosine curve are within 0.01 of each other. And if that's not good enough for you, hit the plus sign a couple more times, and you can see that rectangle has gotten bigger. And plus sign, plus sign, plus sign, plus sign. And I think that's the best we can do. So as long as you are any place in this rectangle here, the red function, which is this 8th degree polynomial, is within 0.01 of the cosine curve. At the edges of what? So there's an inflection point somewhere on the red thing you're talking about? That one? That is the degree 4, yeah. Yeah, Sam is saying that maybe the edge of the rectangle is somewhere near an inflection point here. So does that make sense? Yeah, I mean, certainly the edge of the rectangle will depend on what number you put over here. That's the tolerance that I put in. But it is an interesting idea because if the purple function here decides to change concavity, but cosine hasn't, then the blue and the cosine will start to look very much different from each other. So perhaps there is something going on there with an inflection point. Then I think that's a problem. Yep, that point right there is the only one you can pick. Oh, okay. So your question is, yeah, does this guy right here, does it agree with the cosine curve for at least a little bit, like really agree perfectly? And answer is no. It really only agrees at the one spot we made it agree, which was at x equals pi. It's going to be very, very close, but not equal to when you move a little bit left or right. Good question.
So you said Taylor series were really useful in your
What can I say here? Let's come back and, what's that?
yeah.
Sell you on them. All right, so okay, so first of all, calculators are very good at doing addition, subtraction, multiplication, and division. And even, and I said to Chris that, you know, way back the calculator couldn't handle integrals. To be honest, it still can't handle integrals, so at least not the 83s. It's just doing addition, subtraction, multiplication, and division because it's doing rectangles and things like that. So in order to allow the calculator to do addition, subtraction, multiplication, and division for a cosine function, which isn't addition, subtraction, multiplication, or division, we need to be able to translate the cosine function into a polynomial because the calculator can handle polynomials. So what is your calculator doing when you ask it for cosine of 1? Type in cosine of 1. What is it doing? Does it have cosine of 1 built into its database? I can't imagine it does because you could type in cosine of 1.86432 and it will give you a number there too. So how does it know what cosine of 1 is? It's not looking it up anyplace, and it doesn't have a table embedded in it with all of these zillions of cosine functions. It's translating cosine into a polynomial.
So is it like a really
A high degree polynomial, and then it's giving you this approximation, which is going to be good enough. So I believe that everything that the calculator does, sine, cosine, tangent, ln, e, it doesn't know anything about those functions, but it translates them into polynomials, and polynomials are easy.
So that makes me really not trust some of the things that like
The calculator approximates a lot of stuff.
but I feel like there would be some that are just gonna be like doesn't work with like the way E works.
There's a limit on how much it can, how big the grade area